Hello, everybody. My name is Michelle Thompson, and I'm the CEO of Open Research Institute. We are a nonprofit dedicated to open source digital radio work with a very special focus on amateur satellite work. This presentation is a who, what, when, where, and why about ORI, and then a project summary. We incorporated in California in 2018, and the next year we were designated as a 501c3, or a public charity, in the United States. And we've had very strong international growth, substantial technical and regulatory success ever since. We are incorporated in the state of California. Our headquarters, you could say, is in San Diego, California. This is where our physical location of our remote labs is located, and where most of the shipping and receiving originates from. Our volunteers come from all over the world. We have quite a few from North America, South America, Europe, a few in India, and a number in Japan. Our daily engineering goes on a Slack workspace of about 300 members, and we have an email list with about 280 members. The community is informed through our Inner Circle newsletter. We have about 2,000 subscribers. There's a very simple sign up with the QR code at the right. All of our work is published in GitHub. We have 73 repositories as of today, with 99 contributing members. Our project meetings are usually on Zoom. They are recorded, edited, and published to our YouTube channel. Our website is openresearch.institute, and we're on most social media. Our presentations and showcases and exhibits and demonstrations have been made in Europe, Japan, and North America, and we generally publish articles in ARRL's QAX magazine and just directly in our repositories and our newsletter and on the website. So why? Well, we formed in the very beginning because of bad experiences. We wanted to do digital communications for the amateur satellite service, and there was quite a bit of resistance to this. And we thought that we needed an ethical space for people to work together on digital communications. We needed an enforced code of conduct to make it kind of a safe space for folks to feel comfortable volunteering together. When we say open source, we are using the formal definitions as defined and licensed by the Open Source Initiative. And this is an organization that looks at open source, the definitions, and says, okay, these licenses for this hardware, for this software, are open source licenses. So when we say open source, that's what we mean. When we say amateur radio, this is as defined by international regulatory bodies. We believe that the technical and regulatory heavily depend on each other. And since there wasn't anyone doing what we believe needed to be done with respect to some regulations from the United States, ITAR and EAR, for international amateur satellite collaboration, that was our first priority. And that particular regulatory reform was our first successful project. In 2022, we widened our focus from amateur radio to open source digital radio. So we kept our focus on open source, formal, and we decided that we would tackle digital radio of all types. So the traditional modulations, iterative receivers, adaptive coding and modulation, polynomial phase implementations, error correction, and more. This new focus on digital radio has been super positive. One of the things that we've noticed is that if you approach people, come at them as an amateur radio organization, that people do tend to kind of make some assumptions about amateur radio, fair or not. But when you introduce amateur radio in the context of digital radio, that you get a lot of enthusiasm and you get a lot of new people that want to join, learn more about it, and become licensed. So we think that that was a good approach. It's worked for us. Our organization is composed of volunteers. They're the most important. Project leads, outside collaborators, other organizations, agencies, funders, and then the directors and the executives. We're not a member society, so membership is free, and you get membership by showing up, doing your best, and being ethical. The leaders serve the volunteers. The leaders provide resources and remove roadblocks. people are met where they are in terms of their technical ability. And we often say, you do not have to be an expert to join, but you do have to be willing to become more of one along the way. We have a few to dozens of volunteers active at any one time. As you know, volunteers come and go, and some can afford to spend the time for a little while and then may have other things to do. And some volunteers are very, very active. So we accommodate volunteer schedules fully. Project leads will have in the range of 5 to 10 at any one time. Outside collaborators, we've had 7 major organizations over time and 5 currently that are sort of more formal collaborative relationship. We have 5 directors. We are open to more. And we have 3 executives. These are 3 individuals that have agreed to serve as the executives for the corporation. And we are open to more. What are we? Well, we are 100% project focused. We're an open source research and development firm with a relatively flat organizational structure. When we say research, we carry that out under the principles of open source and open access. And research is explorations, experiments, whether theoretical or practical. We also do development, and this is turning the research ideas and the theoretical into practical things with molecules, hardware, software, firmware, all of which needs to contribute to the advancement of the radio arts. We are very focused on demonstrations and deadlines and documentation. These are things that motivate people to finish things and to move things forward. So we also have products. So we have the research and the development, and we also have a few products. That's our trans-ionospheric radio peripheral and the current RF Bitbanger digital QRP kit. And we look forward to future products coming along over the next year. When we talk about development, research and development, these are things that we achieve through open source. So we're fully dedicated to open source projects, and we firmly believe that this enriches people's lives in at least 3 ways: personally, professionally, and educationally. So our work is used in both commercial and non-commercial ways. There's no restriction placed on the way published work is used, and we've been delighted at some of the uses of our work. The only real restriction that we have is that we do not allow participation for the purpose of creating weapons or for national defense. This would expose us to regulations and realities that would really prevent or chill international collaboration on our projects. So that's the only real restriction that we have to be mindful of. This is a list of our projects. From top to bottom, it's small to large, and generally from inexpensive to more expensive. There's 11 formal projects. We do have a number of other projects and investigations going on at any one time, but these are the ones that are actually named, where we have reports on them, and dedicated folks. Now, the ones that are of most interest to AMSAT UK would be the ones in bold. So Hypharia would be the space segment side. That's what's up in space, or the central node for the communications that we're talking about today. And that would include a polyphase or multi-rate channelizer. And then opulent voice, that's the uplink protocol for our space. It can be used either terrestrially, point to point, or in a multiple access situation like with this particular design. And remote labs, which is where we have equipment available for volunteers to use, so they do not have to buy expensive software, hardware, licenses, things like that. And then worked in here as well is our regulatory work. So that is absolutely important for collaboration moving forward. Regulatory activity, hand in hand with the technical. This is a list of all of the different major achievements and things that we have done, either completed or are actively doing. Remote labs, this is what it looks like. So you can see in the photograph on the left that there's a wide variety of network accessible RF equipment. And what comes with the lab is lab techs, and we have a number of them. I'd like to introduce you to Lab Tech 3, and she is here at an ORI birthday party, so we had a celebration in the lab. Her work was to characterize battery curves for NiCad cells. And the reason that we investigated this is because of the past success of NiCad batteries in space in amateur projects. And this wasn't documented terribly well or really understood. And we had some ideas that, you know what, if you characterize the charge and discharge curves very carefully of your cells, that you can pick ones that have a similar set of curves and that they'll behave very well as a battery. And so she handled this project and learned how to write code in Python, learned a lot of math, about batteries, and also about math and curve fitting. And this sparked an interest in engineering, and she's now a EE major at university. So this is the sort of thing that we try very hard to do: meet people where they are, give them real projects to work on, things that actually can be published, that are actually things you would do in amateur radio, either from a historical perspective, trying to get good documentation, or innovative work that hasn't been done before. The link down at the bottom of this slide will take you to details of all the equipment, network architecture, and remote access to our remote labs, which we are very happy to help anyone duplicate. If you would like to set this sort of thing up, we've done an awful lot of work to make it work for us, for people, make it accessible. Now, on the very top layer of remote labs is the FPGA and radio development boards. And as of today, here are the two that are actively connected to the lab, along with a number of Pluto SDRs. But these are the kind of the larger FPGA and more advanced radio chip versions that we have. So what we're currently using with our projects. The one on the left is a ZCU 102. That's a Xilinx UltraScale Plus FPGA, pretty large, with the ADRV 9002, which this chip is low power, still 40 megahertz wide bandwidth, but it's more for mobile radios. Now, the one pictured in the right is a ZC706, which is a very large 7000 series FPGA, and the ADRB 9009 is a base station style radio chip. Okay, so that covers a lot of space, and these are large enough FPGAs for advanced work. We also have all of the licenses that you need in order to use them. So a full floating license for Vivado. If you have open source solutions that you want to use with these chips, that's totally fine, but we provide the industry standard license. We also have the full license from MATLAB for all of the toolboxes so that you can do any sort of simulation or checkouts of any of the digital communication techniques that you might be interested in. And this is where they're located. And this is how we generally talk in the lab. Over short distances, we use like PCB antennas. This one's from Kent, Britain. And that's pretty much what we do when we're working in remote labs. So if it's not actually connected over a cable from, transmitter to receiver, then we're going short distances over the air with these styles of antennas. So when we talk about opulent voice, this is our uplink protocol, and it is minimum shift keying modulation. It has a 16 kilobit per second high fidelity voice codec. We use Opus and opulent voice, not an accident there. It transmits data and voice without having to switch to a separate clunky packet mode. That was very important to us because we did not like the way that most amateur digital voice modes worked, where you had to switch to do data or images or keyboard. We wanted it to be very modern and efficient, and that's been achieved. This is what it looks like when you are working on FPGA designs. You are describing in software something that will exist in hardware with lots of signals and all of the different software techniques. And this is one example along the way of checking things out. So each of the signals is simulated and confirmed to be working before we try it on hardware. As you know, this is just one part of the process. Once you get to hardware, you usually discover all sorts of other things. that may not have been anticipated in the simulation step. So we help people manage this process, going all through from the basic idea to trying ideas out in maybe MATLAB or on paper or a whiteboard, to writing the code, to simulating the code, to preparing it for testing in hardware, and then setting up the tests in hardware, because the visibility that you have for the signals from simulation to actual integration is different. And we support people throughout that process. So opulent voice status. The modem now works over the air and has the modem, earlier version, has been deployed twice on sounding rocket projects, the RockSat X project with the University of Puerto Rico, and a couple of other universities have used it in the lab and have tested it with different satellite projects. So it's we're very proud of that, and it's really wonderful to work with students and to teach them minimum shift keying or basic digital communications. Super rewarding. Opulent voice, when you look at the code, is composed of reusable VHDL modules. All of the modules are available on our GitHub, and if you go to the link in the middle of the slide, you will find the implementation for the Pluto, so targeting the Pluto SDR. So this will give you the design for the Pluto. If you look over to the right, the upper right, there's a blue waveform, and that's what minimum shift keying looks like. That's the time domain, time series. That's what the waveform sort of looks like. There's actually two different frequencies, and the waveform will shift between the two different frequencies without any jumps or discontinuities. The way that you construct a minimum shift keying signal, it works out this way. You notice it's constant envelope. That is a good thing. You notice that there's no discontinuities. That means that there's no weird phase jumps. It's a lovely mode. It's a little tricky to construct and to modulate and demodulate, but that is why we did this, so that we could clearly show open source example of this modulation, which is very commonly used in space. We deserve to be able to use it too. In the lower right-hand side, you can see there is an image with two peaks, and then the bottom has an image of one. This shows what it looks like when you go from real baseband, which has two images, to the complex baseband, where you have one. This makes it even more useful, less filtering, and more precise control. So that was one of the steps along the way, was going from real to complex baseband. The digital loopback was the first thing that we tested. So this is all inside the FPGA. We're still in digital math land, and we had to make sure that what we were creating, signal that we were creating, was what we expected to receive. Those tests passed. Then we went all the way out to the antenna and did an RF loopback for what's called PRBS, and this is a pseudo-random binary sequence. So that's one of the modules in there, and what it does is just creates a random-looking signal, and that worked. And then we moved to providing arbitrary external data, the things that you would send over the air. And that is now working with a tiny little asterisk, because it looks like, you still need things like a preamble, sync words, and stuff like that. So we are now exploring kind of like the stability of the loops in the demodulator. All that's very active, but the data that you receive is what you sent. So for this minimum shift keying version, for the latest port from the Pluto SDR to a larger FPGA, all of that is going extremely well. Why do we need a larger FPGA? Well, when you start adding things like a framer and a deframer, forward error correction, randomization, interleaving, things like that, you're going to outgrow the relatively small FPGA in the Pluto SDR. And we did. So we bit the bullet and we ported it over to a larger FPGA. This now gives us the chance to include not just the transmitter on the ground station equipment, but the satellite receiver up in the air. That's called Hypharia. This is the uplink receiver on the satellite. It's an open source, multi-rate receiver, and it leverages work from a really neat project, an open source project called Theseus Cores. So they implemented a polyphase channelizer and a polyphase synthesizer, and we took their work and used it to make our design better. So this is in the progress of being implemented on the Xilinx UltraScale Plus processor in our lab and using the 9002 radio chip from Analog Devices. And on the right is just one of the many diagrams that we've made along the way to kind of record the channel plan. Okay, but wait, there's more. The human radio interface is very important. How you talk to the radio, how the radio presents the data back to you that you can use as a human, kind of key. And our human radio interface is called interlocutor. The website takes you directly to the source code. It's a set of Python scripts. It was designed to run on something like a Raspberry Pi 4 or any other computer with a little bit of fiddling. So you have your microphone, a speaker. You're able to chat through a keyboard. You have a display. You can use a command line interface. You have configuration files to start up your radio exactly how you like it, and a web interface. So your opulent digital voice frames are interleaved with keyboard chat, control, and data. And it just works with priority queues. There is no separate clunky packet mode, and the audio is beautiful. 16 kilobit per second Opus codec is much higher quality than Codec 2 or AMBI. This is what it looks like. So you can run the radio from a command line interface if you want to, and all of the functions will work. Or you can call up the web interface. You access it through any browser. You can even use your phone if you want to. It's HTML5, JavaScript, and CSS. This is the communications tab, and it shows you the central window and where you type on a keyboard. You can have a push to talk button in the web interface, or you can use a hard button in on the Raspberry Pi. It's designed with accessibility from the start. On the screen, when you receive audio, you are going to hear it. It's going to play through the speaker live, but you also get what we call an audio replay. So a little UI bubble will appear, and you can replay the audio by clicking that. There are audio transcripts available as well. So if you need to not hear anything or cannot hear, then you can switch on audio transcripts and it will print out what the audio said. It's done locally. There's also text to speech. So if you can't see very well or you cannot spend time looking at your screen, then all of the text messages can be turned text to speech for you. We have been making a huge effort to be compliant with accessibility standards and guidelines, and all of the developers for all of this code are fully committed to doing just that. Anything that improves the accessibility for people that may not be able to see or hear or have other distractions or have motor challenges, we want to make it as easy as possible, and that will help everybody. Now, this is a configuration tab. Config files are edited and saved and loaded and checked for errors on this tab. Some of the changes require a radio restart, but the goal is that your radio starts up completely configured. The configuration runs from top to bottom in the order of most important down to least important. Like, most important is the file name of your config file, your station ID, who you're talking to, the IP address of who you're talking to, because this connects to the modem over IP address, or to other computers. You can talk directly to a computer, and the audio and all of that will show up. Further down is kind of the danger zone of things that you might want to experiment with or customize. But wait, there's even more. Interlocutor will deliver the data frames to the IP address of your choice. Like I said, it can be another computer running Interlocutor for like internet-based communication if you want, but we want to talk to a radio. What helps our radio frames get to the modem? And this interface is called Dialogus. The source code is here. It's an embedded C program that runs on the ARM processor in the Pluto SDR. It takes modem frames delivered through the Ethernet USB port and delivers them to the modem in the FPGA. So it handles that crossover from the programming side, the processor side, to the FPGA fabric. Frames come in from anywhere, and the data, over the IP address, and then the data is delivered to the modem. The modem's called Locutus, and it's in the FPGA. The received waveforms over the air are turned back into baseband frames. They go from the FPGA to the processor side, and the Dialogus handles them going out to the Ethernet port to the human radio interface, or interlocutor. And finally, we do have a demonstration conference server. If you want to see what it would feel like to have a satellite with all of this code running on it, then our demonstration server is called Locus, or the code base is called Locus. Totally open source. It's a Python script that runs on your Linux server, and ORI has a Linode instance set up and running. You can connect to the IP address of Locus. The IP address is right there with your interlocutor program. And then you can hear other operators live audio. And if you have it set up, you can get transcripts, type chat messages back and forth, and see all the control, authentication, and authorization messages. So 2 things that we believe and that we want to bring to your attention. We believe that open source digital radio is the way forward for amateur radio, and that these designs need to be centered in amateur radio work. And you need to give the space and time to learn an experiment with digital communications. A lot of it is hard. A lot of it's unnecessarily hard because it's not taught or explained very well. We really want to help make that an easier process. You can't have digital without analog. Digital exceeds what analog is capable of. It's both and, it's not either or. And we do have to get serious about open source digital radio designs for amateur satellite, and then stay serious about it. The other thing that we want to emphasize throughout all of our designs, there is no room for crappy codecs, for low bitrate codecs. Amateur radio digital voice products for like VHF and UHF, they pretty much have to use very low bitrate voice encoders, AMB encodec 2. These are low bitrate codecs. D-Star, System Fusion, DMR, all of them heavily influenced by P25 voice protocol. Some are essentially a copy of that protocol. Nothing wrong with the protocol, and there isn't anything wrong with digital voice in and of itself. But their low bitrate codec voice quality is pretty poor. This is based on emergency communication worker surveys. Codec 2 is not a solution to AMB really because it's also low bitrate. When we talk about low bitrate, the direct comparison is to a car engine, an internal combustion engine. For horsepower creation, there really isn't much replacement for displacement. If you have a very small displacement engine, there is a limit to the horsepower you're going to get out of it. Codecs, voice codecs are the same way. This is why we say use higher bitrate codecs, open source ones like Opus. This is why we went with at least a 16 kilobit open source voice encoder for our work. This means that 70 centimeters and above is where it's legal. You do have to give up 2 meters for the most part because of bandwidth limitations. Opulent voice takes up 80 kilohertz, the way that we have it implemented today. If you have any questions at all, please ask me anytime, any topic. I really appreciate the chance to present our work and share it here with you today. You can find me at this address, W5NYV@yahoo.com is a direct email address. Please sign up for the newsletter if you're interested in getting updates and articles and explanations and tutorials about our work. And you can find me on social media and LinkedIn as Abraxas3D.